Hey guys, welcome to section 3.3, Centripetal acceleration. So continuing our study of circular motion, we have to understand what that acceleration is and how we calculate it. What we see on the picture here, we have cars at a NASCAR event, and they're traveling at close to 200 miles per hour, which is about 90 meters per second. And so we ask how to describe the velocity and the acceleration of cars like this. And so one of the things we look at is, remember, they have a radius of curvature somewhere over here. So there's a big radius that they are using to travel. And if you remember a little bit, we talked about the tangential velocity is always going to be perpendicular to that. So we're going to really expand on that idea today. So the curve at the end of the track is like part of a circle. Assuming constant speed, the drivers are traveling in uniform circular motion, UCM. That means their velocity is tangent to the track. That is an always thing. The drivers are all accelerating since the direction of their velocity is constantly changing. So let's use a ball spinning around a string. So we'll have ball here at the top and then off at some angle here. And we know we have the center of the circle, and the ball spinning on the string will always be a set distance r from the center. That's the radius. The time it takes to travel around that will still be t, a period of motion. And at each one of these, let's assume it's spinning this way. We'll have a tangential velocity going this way, tangential velocity going straight here, and tangential velocity going this way. So it's really hard to say whether something is positive or negative now at this case, simply because the tangential velocity continuously changes around a circle. So that's something we'll have to be mindful of as we work on some of the problems we'll be looking at. Okay. So if there is no string at all, the ball would simply move in a straight line like so. Cutting the ball being spun in a circle. So let's assume, again, I have my center, I have my dot here, and I have this tangential velocity here. If I were to cut the string, the ball would continue to go that way. It's not going to curve or anything like that. We're assuming we're in space or something. But that velocity will always be tangent to that, and it'll continue on a straight line if we cut the string. So cutting the ball in a circle would mean the ball would travel in a straight line, and it will continue on a straight line until it hits something else. So all of Newton's laws apply. The direction of the velocity is always perpendicular to the radius of the circle at the point, and is tangent to the circle. And in this example, the string is the radius of the circle. So we've kind of already talked a little bit about that, so hopefully not too much new information there. Now here's the centripetal acceleration piece. Here's the thing that we're going to be looking at. Which direction is the string pulling in order to keep the ball in uniform circular motion? Well, the string must pull towards the center, and the string is providing the tension to make that happen. In other words, it's keeping the ball moving. This provides the acceleration towards the center that stops the ball from moving off in a straight line. Centripetal acceleration makes the ball travel in uniform circular motion. So this acceleration is called centripetal acceleration. Another way to say it is center seeking. It always points to the center of the circle. And it is always tangent to the velocity. So the equation for this is going to be something like this. It'll be A sub c for centripetal acceleration and v squared over r, where v here is actually the tangential velocity. And r is obviously the radius of the circle. Once again, acceleration and velocity are always going to be perpendicular to each other, and this is true for any object in uniform circular motion. So once again, acceleration is v squared over r for centripetal acceleration. Tangential velocity is vt, we'll square that, and the radius of the circle is r. And the units for this, again, will be a meter per second squared. That hasn't changed. So we're still going to be able to calculate the acceleration this way. And have a couple of examples here. A car goes around a circular track, has the radius, so I'm given some things here. The radius is 82 meters. That constant speed thing is the tangential velocity here, so Vt is 38 meters per second squared. So it's pretty straightforward. We're going to calculate the magnitude of the car's acceleration. So since it's moving in a circular track, we know we have to use centripetal acceleration. V squared over r. So we have the velocity of 38, the radius of 82. So we should get a value of about 17.6 meters per second squared for the centripetal acceleration. So not awful. Forgot to answer one of the questions. The direction of the car's acceleration, always pointing towards the center. Always pointing towards the center of the circle. All right, last couple of examples. Bike could go around the circular track. I'm given the radius, 63 meters, and here I'm given the centripetal acceleration of 2.3. Looking for the velocity. So just plug in what I know. 2.3 here, v squared there. Make sure we have the squared piece of it. So here's the math that we'll need to get there. So the velocity should be about 12 meters per second. So we'll be able to figure out how fast something is moving based on what we know there. Then the last example, I'm given the acceleration of the object as 5. The velocity here is 2.5 meters per second. So solving for r, do this way for a second. R is just going to be v squared over a sub c. 2.5 is my velocity, and then my centripetal acceleration is 5. Throw that in the calculator. You should get a radius of about 1.25 meters for the circle that's going on here. All right, so not too bad here. So for your assignment, you have the Google Form classwork. There's no quest for this guy. So you have the Google Form classwork and the problem set associated with that found on our topics page. Let me know if you have any questions. Thanks for watching. Bye.